So, to analyze fluid flow, okay, we could take two different approaches. One is an integral approach and one is a differential approach. And we are going to actually follow the differential approach in this course, okay, because it is going to tell you how the fluid flow is at various points in domain, and it is going to give you actually the details of how does the flow look like, and it is important to know what it is. Okay. So, we are going to look at now the differential approach of solving fluid mechanics problems. So, the first thing that I want to define is the acceleration of a fluid element. So, let us say you have some arbitrary flow, and you can define then a velocity field. So, let us say the velocity is some capital V, okay. I am putting that squiggle to show that it is actually a vector, because velocity is a vector, it has a magnitude and a direction, but the velocity will not be uniform, the velocity will be a function of space, it will change with time. So, in order to represent that, I can say that it is a function of x, y, z. So, at every point in space it is going to be different, and time. Okay, so, that is the velocity field that I have gotten. Okay, so, in some domain, but remember V is said to be a function of x, y, z and time. So, that means that at every point the velocity is changing, and it also going to change with time, and my intention is to now calculate what is the acceleration of the fluid element. Now, you could calculate acceleration in two different ways, but let us see first of all velocity. Okay. So, velocity, so since it is a vector, it has an x component, it has a y component and an z component. So, let me write it explicitly. I will say that u is the component of velocity in x direction, which is also going to be a function of x, y, z and t, and is in the x direction, which I represent it as x cap, plus v, which is the component of velocity in the y direction, x, y, z times t, plus w, which is the velocity in the z direction, which is a function of x, y, z and t, sorry, times y cap, z cap. Okay. So, this is basically nothing but the velocity written in a vector form with each component. U, v and w are the components of velocity in each directions, and our intention now is to calculate what is the acceleration associated with this velocity field. There will be an acceleration because velocity is changing, okay, it is changing in space and time. So, you will definitely have an acceleration. The question is, how are you going to calculate the acceleration? You can do the calculation in two different ways. Either you can talk about an Eulerian approach, or you can talk about a Lagrangian approach. Okay. So, the Eulerian approach is that if you are looking at a quantity and you are fixed, okay, so the frame of reference is fixed, you are looking at a particular point and you are looking at the changes, that is what you will have as an Eulerian field, as opposed to the Lagrangian field in which you will be actually following a fluid particle. So, let me give you an example. Let us say you have a you are monitoring traffic, okay, and let us say that you have got you are looking at various vehicles which are moving, and you are trying to find out what is the velocity with which different things are moving, okay, and you reach some junction, let us say some signal, not signal actually, at some junction, you will stay there and you will look at what is the velocity with which each vehicle is going. Okay. So, you are looking at a particular point which is actually that junction, and you are looking at the speed of the vehicles. So, that is what is meant by Eulerian approach, because you are looking at a particular point and then trying to find out what is the velocity field. Okay. On the other hand, let us say you are looking at a particular vehicle, let us say you picked one car and then you are trying to follow that car and trying to find out what is the velocity of that car, then it becomes a Lagrangian approach. Okay. That is because you are picking up an element, a fluid element, or in this case it is a car, and then you are actually following the car. So, then it becomes a Lagrangian approach. Okay. Now, when I have written V as a function of x, y, z and t, I am actually defining my Eulerian field, because I am looking at a particular point and then I am trying to define what is the velocity field. Okay. So, this is the difference between Eulerian and Lagrangian approach, and we would be actually using the Eulerian description, okay, because we have a fixed domain and we are interested in telling how things change at a particular point and in time. And now, I want to define acceleration associated with this velocity field, acceleration. Okay. So, acceleration is going to be a vector which I can write it as ax, x cap plus ay, y cap plus az, z cap, where I want to calculate what is ax, ay, az. Now, let us say you are throwing a stone, okay, and you are trying to follow the stone, which basically becomes the Lagrangian approach, in which case it is very easy to calculate the acceleration, because you will find out how much does the velocity change, okay, in time when you are looking at the stone. So, that is how you will calculate the acceleration. Now, here you have to do the same thing, you want to look at a fluid element and you want to find out how much does the velocity change when you are looking at a fluid element. The only complication is that the fluid element that you are looking at time t, okay, would have reached somewhere else at time t plus delta t, and you are not interested in finding out what is the velocity or the acceleration at that point. You were originally interested in finding out the acceleration of a fluid element at a particular point. So, we can define, let us say, acceleration as the total change in velocity, okay, which I am writing it as dv by dt, where v is my velocity field. I am going to differentiate my velocity with respect to time and going to calculate what is the acceleration. So, this I can write it in a simple form, d by dt with velocity is u times x cap v y cap plus w z cap, which is nothing but du by dt x cap plus dv by dt y cap plus dw by dt z cap. Except that now I need to know what is du by dt, dv by dt and dw by dt. I can calculate that du by dt is equal to, remember u is a function of x, y, z and time. So, let me write d by dt of u, which is a function of x, y, z and time. So, therefore, if I want to take a total derivative, I should be really using the chain rule, which is, so I will differentiate it to time first, that is going to be equal to dou u by dou t plus dou u by dou x into dx by dt plus dou u by dou y into dy by dt plus dou u by dou z into dz by dt. Okay, I have just applied the chain rule because u is a function of x, y, z and t. Now, remember dx by dt is nothing but u, dy by dt is v, dz by dt is w. Therefore, this is equal to dou u by dou t plus u dou u by dou x plus v dou u by dou y plus w dou u by dou z. Okay. So, that is what we have calculated as du by dt, which is nothing but Ax. So, that is the component, okay, of acceleration in the x direction. This can be simplified further. This can actually be written as dou u by dou t plus u dot grad u. So, or rather we have been using the v dot grad u. So, remember our v, we had defined it as u x cap plus v y cap plus w z cap. Grad u is the gradient in velocity. So, grad u is nothing but dou u by dou x times x cap plus dou u by dou y times y cap plus dou u by dou z times z cap. And what I am doing is I am taking a dot product between this velocity vector and the gradient vector. So, if I do v dot grad u, that is going to be a1 b1 plus a2 b2 plus a3 b3. So, that is u dou u by dou x plus v dou u by dou y plus w dou u by dou z, and that is precisely what we had here, and that is why I replaced u dou u by dou x plus v dou u by dou y plus w dou u by dou z as v dot grad u. In other words, we have gotten Ax is equal to dou u by dou t plus v dot grad u. Similarly, you can calculate Ay to be dou v by dou t plus v dot grad v, and Az is equal to dou w by dou t plus v dot grad w. Or combining all of them, I can write the acceleration vector A, which is equal to Ax x cap plus Ay y cap plus Az z cap, which is dou u by dou t plus v dot grad u x cap plus dou v by dou t plus v dot grad v y cap plus dou w by dou t plus v dot grad w z cap. So, if I combine this, that and that, I get that is equal to del by del t of, this is the x component of velocity, y component of velocity, z component of velocity, that is just velocity itself, plus the other three terms combined to give you v dot grad v. So, that is the expression for acceleration. Acceleration is equal to dou v by dou t plus v dot grad v. So, that is the way you have to calculate acceleration in an oil area frame of reference. Okay. So, really this kind of derivative is called material derivative or substantial derivative, or even sometimes total derivative. Okay. So, this basically gives you how, what is the this expression gives you the acceleration, but you could find out the material derivative of any quantity of interest. For example, you can calculate the material derivative for temperature, pressure. So, if you want to calculate it for temperature, that would be, so this is typically denoted with a simple d by dt. So, if you are interested in calculating, let us say d capital T by d small t, where T is that of temperature. Okay. So, that would be nothing but dou T by dou small t plus V dot grad T. So, that tells you what is the material derivative of temperature. What is the physical meaning of material derivative? It is just that if you are following a fluid particle, what is the change that you are going to see. So, if you are going to calculate the material derivative of temperature, if you are following a fluid particle, what is the change in temperature that you are going to see. So, that is what material derivative represents. So, in this boxed expression, if you are following a fluid particle, what is the change in the velocity that you are going to see, and that is nothing but the acceleration. So, that is the way you have to define acceleration. Now, having found acceleration, the next thing that you are going to do is you are going to look at a fundamental law that we will keep using, okay, and that is nothing but mass conservation. It is a very simple fact, okay, unless there is some reaction or there is some source, or unless there is a sink, the mass of the fluid element, mass of the fluid quantity that you are going to look at, it always remains fixed, it is not going to change. So, you basically want to express that fact as a mathematical equation, and that is what we are going to do now. So, what we will do, again remember we are actually doing a differential approach. So, our intention is to write down this fact of mass conservation as a differential equation, and the way you would do it is we will start by considering a fluid element. So, let us say we will take a fluid element. Okay, so, that is a fluid element which is located at the origin of a coordinate system. So, I will draw the coordinate system. So, we will select this as x axis, that as y axis, and this as the z axis. Okay. So, each of the small elements, so each of the small elements, let us say this side is dx, this is dy, and this is dz, and let us say there is some fluid that is flowing, okay, and you are looking at a small domain. So, this is not a fluid element, this is a small element that you are considering in your entire domain, and there is a fluid that must be flowing in the domain, and then let us say that fluid is going to, so we will consider each phase first. Let us say the phase that I am going to shade. Okay. So, that is the phase that we are considering at the first, which is actually a phase that is perpendicular to x direction, okay, which is located in the yz plane. And what I am trying to calculate is what is the total amount of fluid that is going to go through that phase. Okay. So, if I look at the phase x and I want to calculate what is the total fluid that is entering. So, that is going to be, so what I want to write is the total mass that is entering, and the total mass is going to be equal to density times the volumetric flow rate. So, density times the volumetric flow rate. So, the volumetric flow rate is going to be rho times u times d y dz. So, this d u times d time. So, u is the velocity that is perpendicular to the plate, velocity times area, dy dz is a small area, u dy dz gives you the flow rate, multiplied by density gives you the mass flow rate. Okay. So, this is the mass that is going to be entering from this side. Now, I want to again write down what is the mass that is going to leave. Now, in the absence of any other information, the best way to do it is to write down it as a Taylor expansion. So, if rho u times dy by dz is entering the left face, then let us say on the you move a distance dx, the one which is exiting is going to be rho u dy by dz. So, this is what is entering in, this is what is going to be out, plus del by del x of rho u times dx into dy dz. Remember, the area has not changed, you are just looking at what is that has gone out. Okay. So, this is nothing but the Fourier, nothing but the Taylor series expansion. Let us say if you know the value of a function. So, let us say here value of a function at x. So, this is something that you know and you want to calculate what is f at x plus h, where h is a small quantity. You will write f of x plus h as f of x plus f prime of x into h and so on. So, it is basically that fact is that what we have used to write down what is the the amount that is going out. So, let us actually try to make a table now, okay, based on this figure. So, let me make a table. So, the phase that I am considering, what is in, what is out, and what is the difference. Okay. So, if I consider the phase which is perpendicular to the x direction, we said the quantity that is entering is rho times u times dy dz. The quantity that is out is rho u dy dz plus del by del x of rho u times dy dz. Difference we will write as in minus out, and that is equal to in minus out is minus del of rho u by del x times dx dy dz. Similarly, if I look at y, so remember in this case we were looking at fluid that is going to be in through this area dy dz in the x direction, and therefore, we used the x component of velocity, because the fluid element having the x component of velocity u will be entering this domain. Now, if we are interested in let us say flow that is in the y direction, then we would have to look at fluid elements which will have a velocity y component v. So, y component in the y direction, the one which is going to enter is rho v times the area dx dz, and out will be rho v dx dz plus del by del y of rho v dx dz, and in minus out will be minus del by del y of rho v times dx dy dz. Similarly, in the z direction it is going to be rho w dx dy, and out is rho w dx dy plus del by del z of rho w dx dy dz. Oh, I missed something here, this should be dx, because del by del x of rho u times dx, this is del by del y of rho v times dy times dx dz, and therefore, the difference is del by del z of rho v times dx dy dz. Okay. So, this was the quantity, this is the quantity that entered, this is the quantity that was leaving the fluid element, and therefore, this is the difference. Okay. Now, if you have gotten what is the difference, you can add up this difference, and what can you say about this difference? So, see, a certain amount of fluid entered the volume and then certain amount left. Whatever be the difference that you have, that difference, what should happen to that difference? That difference will constitute to change in the mass in that particular element, right. So, in minus out should give rise to the accumulation. So, if mass is accumulating in that fluid element, that means it is going to essentially change the density of that fluid in that volume. So, we can say that if we write down the rate of change of density in the elemental volume dx, dy, dz, that should be equal to in minus out, because if in is exactly equal to out, there is no accumulation, density can't change, there should not be anything else, but if there is a change, that should be reflected as a change in density. So, then we can calculate the rate of change of density is del rho by del t times dx, dy, dz is equal to the sum of all the differences that we have calculated, the one that you see in the red square. So, we have to add all of them. So, I will add all of them is equal to minus del by del x of rho u minus del by del y of rho v minus del by del z of rho w times dx, dy, dz, or simply del rho by del t plus del by del x of rho u plus del by del y of rho v plus del by del z of rho w is equal to 0. Okay. That equation is the equation that represents the fact that mass is conserved. Okay. So, if there is a change in density, that will be seen as a difference in the flow rate between two phases, or if there is a difference in the flow rate, that should be seen as a change in density. Okay. So, this is the equation that describes the mass conservation. We can write this equation in a much more convenient form. Okay. So, remember, the gradient operator that we had was what? That is nothing but del by del x, x cap, plus del by del y of y cap plus del by del z of z cap. The velocity that we have, which I will multiply with density now, is, so we have been using capital V, we will continue with that, rho capital V is rho u x cap plus rho v y cap plus rho w z cap. And if I want to calculate divergence of rho v, okay, that is going to be nothing but del by del x of rho u plus del by del y of rho v plus del by del z of rho w, right. So, that is the expression for divergence, and if you look at this, exactly the expression that you have in this equation, del by del x of rho u, del by del y of rho v and del by del z of rho w. That means, I can simplify and write this expression as simply del rho by del t plus divergence of rho times v is equal to 0, okay, which is a much more convenient form to write the mass conservation. Now, At this point, I will talk about an incompressible fluid. So, incompressible fluid. Okay. Let us assume that rho is a constant, okay. Density of the fluid that you are considering is a constant, and if it is a constant, then it is not changing with time, it is not changing with space. So, if you have del rho by del t plus divergence of rho v is equal to 0, it is not changing with time, and you can take rho out because it is not changing with space. So, that basically gives you the divergence of v is equal to 0, or in Cartesian coordinates you will write it as dou u by dou x plus dou v by dou y plus dou w by dou z is equal to 0. Okay. So, this is the mass conservation equation, and it is very simple to write. Okay. So, because its divergence of v, this is typically also called equation of continuity. So, often equation of continuity and mass conservation, okay, they refer to the same fact, and this particular form where we write divergence of v is equal to 0 only refers to the incompressible fluids. If you look at the expression that we originally had for the mass conservation equation, okay, this is the equation that we had, del rho by del t, and then you have del by del x of rho u, rho v, rho w. Let us write that expression once again and apply the product rules. So, remember we have got del rho by del t plus del by del x of rho u plus del by del y of rho v plus del by del z of rho w is equal to 0. So, that is the equation for mass conservation. I am going to apply product rule to each of the terms. So, the first term remain as del rho by del t plus the second term del by del x of rho u. So, you have to apply the product rule. So, the first rho into derivative of u plus derivative of rho into u. So, del rho by del x into u plus rho into del u by del x plus del rho by del y into v plus rho into del v by del y plus del rho by del z into w plus rho into del w by del z is equal to 0. Let us group some of them. The del rho by del t, del rho by del x into u, del rho by del y into v, del rho by del z into w. So, I will write them del rho by del t plus u del rho by del x plus v del rho by del y plus w del rho by del z plus other terms rho into del u by del x plus del v by del y plus del w by del z is equal to 0. Or simply put, if you look at this, this is nothing but the substantial derivative of rho that we had defined. So, this is nothing but d rho by dt plus rho times divergence of v is equal to 0. So, this is another form in which you can write the continuity equation. Okay. So, we wrote continuity equation in two forms. The first is we wrote it as del rho by del t plus divergence of rho v is equal to 0, or you could also write it as the substantial derivative of rho and then rho times del dot v is equal to 0. So, one good thing is that when you write it in this form, if d rho by dt is equal to 0, that means substantial derivative of rho is 0. So, if you are following a fluid element and if its density does not change, then d rho by dt would be 0, in which case you get divergence of V is equal to 0. Okay. Now, remember the density might be changing locally, but if you are following a particular fluid element and if its density does not change, then is d rho by dt equal to 0, in which case also you get divergence of V equal to 0, which if you write it in Cartesian coordinates, you would have it as dou u by dou x plus dou v by dou y plus dou w by dou z is equal to 0. Okay. So, in this case you will say that the flow is incompressible. Flow is incompressible as opposed to the fluid being incompressible. So, earlier we said that the fluid is incompressible and we threw away all the terms containing derivatives of rho, and then we found that you basically get divergence of V is equal to 0, but you will also get divergence of V equal to 0 if you find that following a fluid element does not change its density, okay, in which case again you will have divergence of V is equal to 0. So, most often the cases that we will consider would be either the flow would be incompressible or we will take the fluid to be incompressible, and in either case we will have divergence of V equal to 0, and that is the equation that we will use.